Okay, I don't want to use up any more of our time. So welcome everyone to the Frontier Technology and More poster session. Appreciate you joining us today. We have quite a lot of great presentations. So I'll just jump right into it and we'll go through all the presentations. If you have questions for any of the speakers along the way, feel free to type those into the chat. If all goes well with the speakers keeping to their short times, then we will have time at the end for some questions and discussion. We will keep this session to a tight 2 p.m. cutoff for everyone's schedules. So with that, we'll go ahead and start this. So Ethan Williams, would you like to begin?
Thanks. So this lightning talk and posters summarizes the results of kind of 3 separate projects in collaboration with the University of Alcala and cable company Marlinks. Next slide, please. So we're working with the new technology, frontier new technology, distributed acoustic sensing, which I think many people are now familiar with, repurposes fiber optic cables as dense arrays of thousands of linear strain meters. And there are many fiber optic cables pre-existing on the seafloor. And so here we've leveraged 2, one offshore Belgium and one in the Strait of Gibraltar. Next slide, please. Just looking at the raw data from these cables, the signals are very interesting. You see a superposition of fast waves and slow waves propagating across the cable from multiple directions, though ambient noise is very messy. Because we have a linear array, we can take a 2D Fourier transform to get a frequency wave number domain view of our data. And we can very clearly see that there are 2 wave groups, seismic waves propagating in the vicinity of 1 kilometer per second, and ocean waves much slower, around 10 meters per second. Next slide, please. And if we do ambient noise cross correlations, we get not only the kind of expected surface wave phases that we use for surface wave tomography typically, but also distinct ocean wave phases. And so what we're basically looking at is direct pressure loading of the seafloor. So effectively high frequency, phase coherent seafloor compliance from ocean surface gravity waves that we can observe in extraordinarily high resolution that you can't normally do with a broadband OBS array. So next slide, please. So the 2 applications we're developing here are for seismology and oceanography, kind of making an argument that there's a broad interdisciplinary potential in having distributed acoustic sensing deployed in the next generation of ocean bottom seismic monitoring technology. So for seismology here, using these Schulte waves, we can very easily just apply a standard beamforming approach and develop a 2D shear wave velocity model of the shallow subsurface. Next slide, please. And for the oceanography part, we observe very clearly that there's a Doppler shift in the ocean surface gravity waves along the array, with waves propagating more quickly in one direction than the other, indicative of them propagating in a current. Next slide, please. And we can use the cross correlations. Oh, go ahead. Yeah, thanks. The cross correlations and the ocean wave phases in the ambient noise cross correlations and look at the time lapse and very clearly observe that the travel times change on a 12-hour period. And therefore, by stretching the waveforms, we can recover the current speed along the cable. So there's potential here for spatiotemporal monitoring of ocean currents. Next slide. And so to conclude my 3-minute super lightning talk, ocean bottom DAS offers some pretty broad interdisciplinary value beyond conventional seismometry, with passive Schulte waves being used with only 1 hour of data very easily for shear wave velocity tomography, and the simultaneous ocean wave observations being used for current speed, potentially even wave height estimation once the amplitude measurements are better calibrated. And if you'd like to talk more about this, I encourage you to visit my poster or email me. And there's many other applications we've been exploring as well along these lines. Thanks.
Thank you. All right, we'll move right along. Martijn?
Yeah, thank you. All right, so my name is Martijn, and I'd like to show you a simple yet elegant deep learning method for denoising your DAS data. Next slide, please. And I'll explain the main idea based on this picture of a zebra. So here I put 2 patches on the image, so you can't see what is underneath. For patch A on the right, you can kind of make an accurate guess of what the main structure of the stripes under the patch is, right? This is because the stripes have a long range coherence that can be interpolated. On the other hand, the bushes on the ground are much less coherent. And so you cannot really predict what is the exact structure underneath patch B, other than just that it's probably green. Next slide, please. And the same thing applies to distributed acoustic sensing data. Most of the signals of interest are coherent in space and time, like we've seen in the last presentation, but also in this little earthquake that you see on the right. But on top of the earthquake signal, we have incoherent noise, which we'd like to get rid of. And this noise sits in the same frequency band as the earthquake. So this is filtered between 1 and 10 Hertz. So we cannot really separate the signal from noise by traditional filtering techniques. But we can do this by leveraging the concept of what's called J-invariance. Next slide, please. So we will be applying this method to earthquake data recorded by 2 submarine DAS cables that are deployed offshore Greece. And after some really basic pre-processing of the data, we are ready for additional denoising using our deep learning technique. Next slide. And this works as follows. We take a set of waveforms recorded by neighboring DAS channels, and we set one of those to 0. And then this set of waveforms goes into the UNet convolutional neural network. And then the target for the network is to predict the waveform that we initially set to 0. So to bring us back to the example with the zebra, blanking a waveform is essentially equivalent to putting a white patch on the image. And the neural network then tries to predict what is underneath that patch by looking at its surroundings and trying to interpolate coherent patterns. Now, since incoherent noise cannot be interpolated, it is trying, because it's not cannot be interpolated, it is not included in this reconstruction. And at inference time, we can then reconstruct each DAS channel one by one to recover a free, and reconstruct it is free of noise. Next slide, please. Okay, so here's an example of an earthquake with a rather mediocre signal to noise ratio. And after applying our deep learning methods to these waveforms, we preserve the coherent earthquake signals while suppressing the incoherent noise that you can see just before the earthquake, before around 20 seconds. Next slide, please. And we can also see this in individual waveforms, especially the one here at the bottom, which shows a much lower noise level while the earthquake amplitudes are well preserved. Next slide, please. So just to conclude this, we propose a self-supervised deep learning method for blind denoising of DAS data, meaning that we don't need a clean ground truth or make any assumptions regarding the statistics of the noise. And also the model is very fast to train and requires very little data, and can even be trained on a single earthquake. And then after training, we can separate signals of interest from the noise, even if they share the same frequency band. And finally, signal coherence also improves substantially, which may aid coherence-based seismological techniques like beamforming and template matching. Next slide, please. Casey? Uh-oh. Kristen, could you back up?
Yep. Let me pull the slides up. Hopefully I can.
It's a good thing that you girls practiced on this just a few minutes before.
Okay. You guys see my screen?
I do not, because I have this issue that I cannot switch, but I presume that. So does anyone see the links and the last slide?
Yeah, does anybody see my screen?
Yes, so it's the same as in the last session. You have to go to the view options at the top and select the screen.
Okay, so some people do not have that button. Like me, I do not have that at the view options button. But okay, I presume that some people at least will see a few links on that slide. So one of them is a repository where all the pre-trained models, data, and codes are available. And the second one is a preprint of a manuscript we just submitted. And now I'm seeing something else.
Okay. Are you seeing my screen now?
I'm seeing conclusions from someone else. This is from Ethan.
Oh, okay. So I'm on the wrong.
Yes. Yeah.
I don't know how far.
And stop.
There
Yeah.
Okay.
Okay. Well, this is just what I mentioned. It's everything that was on the poster and also in the sliding talk is online, so you can try it yourself if you like. And you can contact me via email or Twitter if you have any questions. Thank you.
Okay, it looks like the next presenter.
All right, I am ready. So hello, everyone. My name is Sirawich Pipatprathanporn. You may call me Pete. Today, I'm going to present my project working with Frederick J. Simons, which is my advisor, on seasonal variation of acoustic noise in the ocean recorded by the MERMAID. The left photo is a picture of MERMAID, which is a floating hydrophone. And the right picture is the map of the MERMAID, which is in the middle of the ocean, labeled as the green triangle. And the other small triangles are stations that have ever reported any earthquake. Next slide, please. So how MERMAID works? So it floats at 1500 meters depth, recording acoustic pressure variation in the water column. It captures noise, local earthquakes, and teleseismic earthquakes, and reports teleseismic waveforms for tomography. It is not normally recovered, but we caught and redeployed this one. Could you click more, please? There's 2 more bullet points, thanks. And we report all earthquakes in the buffer, and then analyze the noise, its temporal variation, and its cause. Okay, next slide, please. So here are the earthquakes. So we found 213 earthquakes in the buffer, 10 of which were reported right away by the MERMAID, and the others were found later by me. And the right figures are the distribution of earthquakes by the epicentral distance and the magnitude, and the yellow stars are the earthquakes that are reported by the MERMAID. Note that the magnitude is higher than those unreported, although there are some unreported earthquakes that have very high magnitude. Okay, next slide, please. And here's the spatial distribution of the earthquake that I can match. Most of them are around the Pacific Ocean with a few exceptions. Next slide, please. So after we remove all the earthquakes from the buffer, we calculate the power spectral densities of the ambient noise and analyze the temporal variations in different frequency bands. And by that, we compare with the wave watch, which is an ocean wave model. And then we correlate the surface driving force with the MERMAID noise. And we found that the MERMAID noise is highly correlated with at the double driving frequencies, which is consistent with the double frequency mechanism, so that we can say that the weather generates the ocean noise. Okay, next slide, please. All right, so could you click one more time, please? Oh, thanks. Okay, so the left figure is the spectral density comparison between the MERMAID, which is the red curve, and the wave watch, which is the black curve. And we can see that if we shift the wave watch curve to the right by a factor of 2, which is like multiply frequencies by 2 and then shift up the spectral density, you can see that the spectral density align pretty well. And it also shows in the right figure, which is the energy correlation coefficient plot over a year. Notice that the wave watch frequency is on the x-axis and the MERMAID is in the y-axis. And the correlation coefficient is highest along the double frequency line, which is marked as the white dashed line, which suggests that the noise we see deep down in the ocean recorded by the MERMAID is indeed generated by the weather at the surface. Okay, next slide, please. So in conclusion, we can say that the MERMAID is capable of recording the ambient noise in the ocean in addition to the earthquake. And this is an ongoing project, and there are also other mermaids floating in the Pacific Ocean as well. And I'm going to compare these records by this mermaid to other mermaids as well, and try to compare with the synthetic seismograms later in the future. So I will conclude this presentation, and if you have any question, please contact me at sirawich@princeton.edu. Thank you for listening.
Thank you so much, and sorry about any issues we've been having. We'll just keep going. Thanks, Kristen.
Oh, of course. Okay, up next, looks like Victor.
Here I am. Okay, thank you very much. I have my 4 minutes. Let me first initiate my presentation apologizing, because my original plan was to present you some news, but unfortunately, due to the situation that most of you know, we were unable to run with the project. So essentially, what I want to present is a lot of problems that we have here in the region, particularly with the detection and the monitoring. First, let me tell you what is part of the mission of the PRSN. PRSN is the Puerto Rico Seismic Network. And one of the most important parts of our mission is the detection and the cooperation with the Tsunami Warning Center. And particularly, we need to have a comprehensive network to detect any threat to the island, and including the Virgin Islands. So that's part. Thank you. Here is the problem. So go back, please, one moment. Okay, thank you. Here is the problem. You can see the island of Puerto Rico and the Virgin Islands, and a couple of fault systems around. The prominent fault systems are offshore. That's the main problem that we have here in the island. Most of the big events historically happens in that faults offshore. In the north is the Puerto Rico Trench, in the south is the Muertos Trough, but we have many more offshore faults. So we have a problem because we need to detect and we need to monitor those faults that are outside the island. Next, please. So that is, you know, what are the threats in the island? So, you know, the hurricanes is one of the most important threats. As an example, 3 years ago, we were affected by 2 big hurricanes, category 5 both. So next, please. And as a result, that happens to the infrastructure, electrical, the communications, a lot of flooding, a lot of problems. And next, please. Particularly the monitoring system in Puerto Rico was affected tremendously. You can see what happened with the siren system, what happened with the seismic station, what happened with the geodesy stations, tide gauges. So essentially, most of the 90% of the infrastructure of the detection infrastructure was destroyed due to the hurricane. Next, please. But fortunately, using some funds from the federal government and the local government, we initiate a good project to reestablish and reinstall the seismic network. That's an example of how the station looks like today. 30 broadbands, GPS, and satellite stations are actually installed in Puerto Rico and Virgin Islands. Next, please. That happens, that the seismicity around Puerto Rico, you can see most of the seismicity offshore. That's the problem that I tell you. In the small figure in your right, you can see what happens 1 year ago. A seismic sequence very active affected the island. The main event happens in January 7, magnitude 6.4, many damages. A lot of millions of dollars lost in that time. That sequence is actually active. Next, please. As a result of that big event, you can see what happens to the infrastructure of the island, the schools, the churches, homes, even the geological, beauties here in the island, essentially many things were destroyed due to that earthquake. Next, please. Okay, so here is what we need. So essentially, as mentioned in the first slide, we are calling for support. Essentially, that is the idea behind my presentation. So we need to have something to monitor offshore, something that helps to improve the seismic network or the detection system that we have here in the island. So probably some equipment or some devices or technologies that help us to understand all the problems that we have around. In addition, we need to improve the early warning system that we have in place in the island. So probably we need, and we are consulting with some companies because I guess that the idea is to have some sound detectors, something that provides some help because we are exposed to landslides. And landslide happens in the history. So we need to have something. So probably the sound technology is a good candidate. So if you have any idea that will help us, please let me know. And finally, we need to improve the geodesy network, and particularly something offshore. Inland, we have a very comprehensive, a very good network, but offshore, definitely we need to improve that. So that's my presentation. Thank you very much.
Thanks so much, Victor. And good luck with the next steps on that. Wayne, would you like to, I know you have just one slide.
Just one slide, because last time I gave one slide, it took me half an hour anyway, so I'll try to be shorter. So this is actually, it's not really frontier science in a way, because we're using quite old technology in the short period OBSs, but there have been a lot of these deployed around, and some of the things we want to do with them depend upon orienting them like we do with broader band instruments. And we discovered a problem with these that seemed to be sort of a generic problem with short period and local networks. And so we wanted to communicate this, and we're still looking into the reasons behind it. It started with a network that we're working on in the Lucky Strike segment of the Mid-Atlantic Ridge, where we only have 5 stations. So we wanted to get the full 3D waveform in order to do focal mechanism calculations. And we found after a lot of looking that there was something wrong with the orientations we were getting. And so we started looking over a broader range. We're using what's called the P-pole polarization method. You're using P-wave polarization, where you take an instrument and you have an earthquake somewhere. The earthquake has a back azimuth that's expected. You could see that in the upper right. If the event's coming in, let's say from the northeast, you expect a certain back azimuth, let's say 30 degrees with respect to north, but you actually measure with respect to the instrument a different back azimuth. In this case, it would be something like, let's say 120 degrees. And to calculate the orientation, you subtract the estimated from the expected, and you get an orientation estimate. And to get some sureness of this, you need to do this over a variety of back azimuths. And what we discovered when we did this over a variety of back azimuths was that we were getting the same estimated back azimuth for many, many different real back azimuths, as you can see in the middle plot on the left. So here we've got on the bottom axis, the x-axis, we have these expected back azimuths that has to do with the physical geometry between the station and the event. And so you'd expect kind of a linear relationship between this and the measured back azimuth, or the estimated back azimuth, which is on the y-axis, but instead it's flat. It's the same value. And when you take this into an estimation of orientation, you get kind of nothing useful. Oops, that just disappeared. You're telling me I should stop talking? Okay. So I won't go too much longer into it. We tested this same code on broadband stations, and it works. We tested this code on stations that had both broadband and local. It works on broadband data teleseisms and not on local. We tested this on, if you see in the bottom, we showed maps of different sites we tested on, so different types of OBSs, not just ours, and even land stations. And not always, but quite often we get the same result. So it's a little bit of a warning right now that you need to be very careful when you try to interpret local seismic data. Even if you could orient your instruments using another method, let's say air gun shots or whales, it doesn't mean that the stuff coming through the seafloor will be properly oriented for you to use it as a real 3D wave field. So we're looking further into this. I have a 20-minute talk or a 15-minute talk that's recorded if you want to see more about it. And if there's anyone that wants to work with us on this, they're quite welcome.
Thanks, Wayne. Sorry about that.
It's just a sensitive mouse click.
Yeah.
So not 30 minutes, great. And now, John? Let's see.
Now I got it.
Okay, got it. Great.
The authors of this poster are myself, John Berger, Monica Kohler, and John Collins. The comments are relevant to the establishment and operation of a global ocean seismic network. The approach, however, is also relevant to deployment of OBSs for campaign-style studies. Next slide. Electronics have been evolving at a very high rate, consistent with Moore's law to date. This table shows the evolution of several systems over the last 30 years. Our oldest OBSs were built at the beginning of this record. One good example is the size of the features of the chip. Over 30 years, integrated circuit features have increased by a factor of 2 million times. If it may be surprising that on average, consumers buy a new iPhone every 2 to 3 years since the capabilities evolve rather quickly. Flip phones have evolved enormously. Next slide. In a collaboration with Nanometrics, we've integrated our OBS electronics with the Nanometrics Pegasus data logger. This has resulted in a major reduction in power consumption on the seafloor. The abalone system can hold 70 double-D lithium batteries for a deployment that lasts approximately 1.25 years. With the new electronics, this drops to 2 double-D cells and 4 if the data are telemetered continuously. The power required is dropped by a factor of 30. Next slide. This photo of the newest OBSs we've designed, constructed, and deployed many times. The instruments are now 12 years old, which is much more than one of the cycles in the earlier slides. It's very expensive to avoid a continuous evolution of electronics. For the oldest of our instruments, 30 years, most of the components are no longer available. Next slide. Finally, it's important to begin the design and construction of autonomous oceanographic ships that are capable of maintaining systems at sea. This would greatly decrease the cost of operating a global ocean broadband seismic network, for example. When in transit, the ship could map, for example, the seafloor with a modern multi-beam system. Thanks very much.
Thanks, John. Very cool ship diagram there. All right, so everyone's been great on keeping the time, so we'll just continue on with our last speaker, Andrew Newman.
All right, thank you very much. So I'm going to speak today briefly about seafloor geodesy. And so we all know that geodesy is a tool that we've been using for measuring deformation for quite a while. Those activities have primarily been on land, however, in part because the instrumentation is good there and also extremely cheap. However, offshore, 90% of our plate boundaries exist, as well as 100% of our tsunami generating sources, or I should say sites occur. With a seafloor geodesy, you have the potential for making measurements of tectonic deformation, volcanic deformation, things like submarine landslides, as well as things like subsidence associated with offshore hydrocarbon extraction. Go ahead and switch to the next. So I, with a group of others, were able to put in for a proposal. This is born out of actually what was originally towards the mid-scale research infrastructure program within NSF. We were able to get funds, about $5.5 million, for the procurement and testing of a small network of, or I should say, a small pool of seafloor geodetic tools. So these tools include enough for 16 complete sites that include both GNSS acoustic as well as seafloor pressure. And so with these sites, we should have the capability of making sub-centimeter horizontal measurements for long-term deformation associated with things like tectonic deformation or the likes, and shorter-term vertical deformation that's on sort of the same scale using the pressure sensors. So that would be useful for short-lived volcanic events, things like submarine landslides, or I should say rapidly moving submarine landslides, as well as volcanic deformation. With this, we're also able to acquire 3 wave gliders for data collection. And so these things are autonomous offshore vehicles that move due to the differential in wave motion on the sea surface and that just beneath it. These interrogate the sea floor and relay data back to land. So what we have right now is equipment for the building, but we don't have equipment for, we don't have money for deployment, operations, maintenance, or training, nor do we know exactly where we're going to go with this yet. So next slide. So what we've been able to do is get a seafloor geodesy workshop funded in order to get community feedback on what to do with the pool, as well as a few other things. This workshop was originally planned for last summer, but will now be held in the near future as a 3-day meeting, so April 6th, 7th, and 9th. The workshop goals are to identify the active community, to get feedback, I said, on the pool usage, to assess possible targets, foster the equitable inclusion of this workforce, and inform on new technologies and get feedback from the community on these new technologies or capabilities that we can use for future deployment. We have a white paper set of presentations coming up very shortly next Thursday. And if you're interested, you can register for both of them at seafloorgeodesy.org. Likewise, we're looking at getting continuous funding through NSF as well as NASA and USGS to explore continued development. One last slide, and just as a quick advert. Tonight at 7:35 p.m., Mark Zumberg at Scripps, who is managing the building and testing of these sites, will give a 15-minute presentation on more of the details of the instrumentation, as well as the status. Thank you.
All right, thanks so much to everyone. Great job keeping the time too. I was not sure about that with all the number of slides. So well done. We have plenty of time for questions. So thank you for that. We'll just keep it. You can go into gallery view if you'd like, just and feel free to share your video. If you have any questions, you can type them into the chat or raise your hand and we'll call on you in order. Anyone want to start us off with any questions? Oh, Jim, go for it.
Yeah, thanks. I had a question for Wayne. It's a really interesting kind of discovery and set of observations. And so I had a little bit of a hard time figuring out whether it's entirely the frequency band, do you think? Meaning, does this also fail on teleseismic events that are in those higher frequency bands, or do you think it's more of a local signal problem, and that the technique actually did work in the teleseismic data in that high frequency band?
Well, I haven't seen teleseismic data in that high frequency band. I guess when we looked for the Lucky Strike data, we didn't find any teleseismic earthquakes that gave us detectable earthquakes on our short period OBSs. So we just looked at the high frequency things. We just looked at the local events. When we looked at axial seamount on the stations that were mounted there, which are a little bit broader band, the short period OBSs, we got good results for the teleseisms and then bad results for the local in general. But I I can't see why it would be just a local event. So I would assume it's something to do, our first idea is that it's something to do with reflectors, near surface reflectors, because a lot of these are volcanic regions that might be dipping reflectors that could be steering the arrivals or something like that. And we're going to have to do some waveform modeling to do that. We're also going to do some measurements in non-volcanic areas, like we want to get data from the Blanco transform to look at that to see if the stations worked better there. And I don't think it's the fact they're local, but we don't know yet. So maybe there's something to look at that at there.
Okay, thanks.
Thanks. I think we'll go to Sean next.
Thanks. I have a question for Pete about the MERMAID data. That's looks very amazing that you can detect some earthquakes that usually ignored by traditional seismic stations. But on your poster, I just wondered. So it looks like you have the minimum magnitude detected at about 4.6. But if you because some of your MERMAIDs are kind of closer to some subduction zones, can you see even smaller earthquakes with the even closer distance?
I wish I could answer this question, but I don't know much about the other MERMAIDs, and because right now I have only matched the earthquake arrivals we found in the buffer with known earthquakes, so that there may be some local small earthquakes that are not on the database or not on the catalog, so that I cannot match with. And there's still some interesting signals that is very small and I cannot match with any earthquake events. So that may be my something that I can do in the future. Right, thank you.
Thank you. Any other questions? Feel free to, sorry, I haven't quite met you yet, so I can't pronounce your name correctly. I'm gonna mess it up.
It's okay, it's a hard one. It's Itzhak.
Itzhak.
So another question for Pete. If I understood correctly, what you're measuring with the hydrophone is actually pressure perturbation, so it's basically T waves, right?
I forgot to unmute. So it could be T-wave, but it also recording all kind of acoustic signals. It could be acoustic signal that is generated by either S wave or P wave or either surface waves that travel in the ocean floor.
Okay, so my follow-up question is are there any azimuths or locations where you detect more earthquakes or more low magnitude earthquakes, and regions where you do not detect? I mean, do you find a correlation with the bathymetry or any other features?
So I haven't done any kind of that. I just try to see if the MERMAID is capable of recording the earthquake signal, and I try to see if there's any earthquake that is not reported by the instrument. So I haven't looked into the bathymetry of the ocean floor or which direction has more earthquakes. All I know is that the earthquakes that I can match with the known database and I can plot with on the map that I have shown you earlier. And that's the best thing that I can answer for your question. I'm sorry about that.
No, it's okay. Thank you.
You're welcome.
Thanks. Anyone else? Megan, it looks like you had unmuted. I don't know if you had a question.
Oh, yeah, I couldn't get my video to work. Oh, there it is. I was just curious what catalog you're using. You said that when you were looking for smaller magnitude events, and I guess follow up for the last two questions, which catalogs do you look at?
I use the one from IRIS.
Is that the ISC?
Let me see. Not sure which one is. I use the one from that is published on the IRIS website. So let me see which one.
Maybe we'll give you a chance to look that up, and you can post it in the chat there for everyone.
Yeah, that's fine.
I'm curious for the two early DAS presenters. I know that this is a sort of a burgeoning field, and but there's a steep learning curve with so much data that you have to handle. So I'm curious, the way that you presented your work, it makes it seem very welcoming. But what were your strategies to get over that fear of big data? Martijn or Ethan?
Yeah, well, I think many of the experiments are relatively short term, so of the order of, say, 1 or a few weeks. So that will keep the data volume at least manageable. Because if you go too much longer, they will start running into issues with, well, where do you store your data when you produce about 1 terabyte per day per fiber. And then, yeah, even basic processing like bandpass filtering, well, that takes a lot of well, power and resources to even do those kind of things. So fortunately, I could work on some data that was already cut up in small little bits, so you don't have to slice into too much data at once. And but yeah, there's something that I've noticed that I had to wait a long time to just download the data from the server to work with it. And yeah, so there's definitely some gains to get on having efficient pipelines in processing all that. Ethan?
I would agree. And similarly, we've worked with severely decimated versions of our data sets, in particular for the ocean wave work, where I showed that 4.5-day data set from the Strait of Gibraltar. All the ocean waves are at a maximum frequency of maybe 0.3, 0.2 hertz. And so we can work with a 1 hertz data set very easily, and that reduces it from terabytes to gigabytes.
Yeah, very different from the 500 hertz frequency sampling frequencies that I've worked on so far.
Yeah, maybe there's some sort of resources that can be done at the data center level in order to sort of smooth out some of those barriers to using some of the data. Any other questions from the audience, from speakers?
I have a question as well for the DAS presenters. So DAS is brand new, and I don't think I have much of an understanding of it. And it seems, if I understand correctly, that a lot of the work that's being done with DAS right now is just trying to understand what signals we're seeing and how to interpret them. And so I guess I have kind of a basic question in terms of, I know one of you mentioned that you observed an earthquake during one of the DAS deployments. And I guess, do you have any comment as to how earthquakes are observed on within DAS data? Like how, I guess, does it translate in terms, do you see a P wave? Do you see an S wave? Kind of, is there any more, is it intuitive to see these signals, and how does it translate to, more traditional seismogram from an OBS?
Yeah, so with DAS, we do register both body and surface waves. But due to the measurement principle that we measure strain or strain rate and not particle motion, the slower waves tend to be amplified. So we see surface waves much better than body waves typically. For underwater DAS and submarine DAS, very often we don't see very clear body wave arrival. For on-land experiments, I've seen many more examples of clear body wave arrivals. Yeah, how to exactly interpret strains in terms of particle motions, there are some ongoing work about that, on how can we convert strains back into particle motions, something that we're familiar with, or how do we work on strain directly. But things like beamforming and such, they also work directly on DAS data. It's just that sometimes you beamform a signal that is something different than what you initially thought of. That's the origin of the signal, because of the sensitivities that strain has compared to particle motion. But yeah, there are many. So, for instance, in Solid Earth, the journal, the EGU journal, there's a special issue that is coming out where there are a few studies that study specifically, what is it that we're measuring and how does DAS compare with seismometer arrays.
Great, thank you so much.
I can put a link in the chat.
That would be great, thanks. Any other questions? John and Andrew, is there going to be sort of a coordination effort between sort of a global broadband seismic network in the oceans and global seafloor geodesy? Some overlapping goals there, I'm sure.
I don't know who should take this. Maybe I'll speak first since I'm unmuted. That would be interesting. I think they certainly have a lot of synergistic interests. However, one of the fortunate features, at least with seismometers, is like for the GSN, is that you can see earthquakes without being directly on top of them. Whereas for getting good deformation signals, from geodesy, we need to be more proximal. So I think, though there's a lot of synergy, certainly in offshore work, there's also there are very specific and different requirements for some needs.
Yeah, I think also the fact that both of these use these liquid robotics, Boeing gliders is an interesting thing. One of the projects we have with Office of Naval Research right now is looking at other sources, low Earth orbit satellites for moving data. We could move data a lot faster than we do over traditional Iridium, and I think that would help all of us if we could evolve a better, higher speed communications link over the coming years. So I think there's a lot of consistency between the requirements for both systems.
Yeah, certainly it seems like the advancement in technologies and materials sort of outside of the sensors themselves have both been to the point of being very useful for both of these applications.
Just one other comment. I think that an autonomous vehicle would be great for geodesy too. That would really lower costs and allow you to examine the sites more often.
Just as a response, so we do have wave gliders which are autonomous. They require a little bit of piloting to get things out, get out of the way if a large ship is coming through. But we are using those now for GNSSA. It would be really nice to have autonomous underwater vehicles to go down and get higher rate information that we'd want, let's say, from the pressure sensors.
Yeah, in that regard, John Collins is working on a blue-green light system that has a lot of bandwidth, and that'd be good for the GSN as well, because the data we can telemeter to Iridium is pretty low, 1 hertz for 4 channels, and you have to leave a lot of that data on the instrument. You can get short bursts, but in order to get broadband data, a system like that could be launched again from an autonomous vehicle. From an autonomous vehicle could carry a lot of that data back to shore.
All right, there seems to be some good resources popping up in the chat there about the special issue on DAS and more about the catalog for the earthquake data. And of course, we welcome everyone to continue conversations and discussions on the event page or in the individual posters, where you'll find longer recordings and more slides for all of these, and to continue discussions with speakers. Are there any further questions? We still have some time. And yes, so Andrew put in the link for the seafloor geodesy workshop that's coming up very soon. Okay, well, unless anyone has any final words to say here, I mean, we will be having plenty more presentations this evening during the Harnessing New Technologies session from 4 to 8 p.m. Eastern. I encourage everyone to attend that and continue these discussions further. With that, thank you again to all of our speakers and presenters, and see you soon at our next session.